From Universidad Federal de Minas Gerais in Brazil, and who is going to talk about monotonicity formula and the long-time behavior of Schrödinger equation. Please, you can start.
Thank you for the introduction, and thank you to the organizers for inviting me here. It's my first time in Mexico, so I've never been here before, so it's been a pleasure to know the city, to know you all. And this talk is going to be about Schrödinger equations. I know it deviates a little from the previous talks today. And nevertheless, I try to make it accessible to no-niche areas. So in the sense that I hope many of you can understand what I'm talking about tonight or today. Is it still day, right? Yeah, it's still day. So first of all, I'm from Minas Gerais, Belo Horizonte, the capital of 7-1 against Brazil. And for many of you that don't know the city, this is how it looks like. So yeah, it's not Mexico City, it's not that big, but it has some view, some church, some lake. And now that I have your attention, we can talk about mathematics, right? So first of all, I'm going to give you an introduction about what problems I'm considering, what I mean by so what's the opposedness, we're going to talk about PDE, so a little bit of PDE talk. And then we enter this main topic of the talk, which is called the monotonicity. So what I mean by monotonicity, how I'm going to use it. We're going to talk about scattering, but basically nonlinear scattering. So this is going to lead us to a scattering criterion and then final remarks. I try to make it short because you probably want to go drink something else after this. So I can start. So basically, we work with the so-called nonlinear Schrödinger equation. So it has this Laplacian here, it's nonlinear because of this term, and it's an evolution equation. So it's Hamiltonian, so you can put any language you want here to describe this equation. Typically, we work with the initial datum in Hilbert spaces, for example, and Sobolev spaces. It's not mandatory, but it's typical in this field so far. And because of physical reasons, of course, because of the energy spaces, for example, H1, so we tend to use some physical spaces as well. So basically models, for example, optics in the so-called Kerr media. So it's the media in which, for example, we have a wave traveling, a light wave, and the refraction index of the media is not the same for every amplitude. So different amplitudes have different diffraction indexes. So it happens to, so the most common case is the cubic one. So it happens when this Kerr media comes into sight. So it gives us a nonlinear behavior for the wave. So for example, they try to use this, they're still trying to use in what they call planar waveguides. So I want to send a pulse in a fiber optic. And this pulse should last as long as possible so we can have, for example, internet or any form of communication, right? So they're still trying to do this. There's other ways to do besides finding waveguides in this kind of optic media, but it's still developing. But of course, it happens, it appears in other settings, for example, in Bose-Einstein condensates. So the nonlinear Schrödinger equation appears as the limit of many bodies and some kind of limit. We're using basically a system of many bodies with a linear interaction. If you take a limit, it becomes nonlinear. So there are many applications. For example, gravitative waves on water. We have relativity applications in relativity. So it's a very ubiquitous physical model. We're going to talk in this talk about this classical Schrödinger equation and also an inhomogeneous version of it. So basically, there's a potential here, 1 of x to the b, which is singular, the origin somehow, it decays at infinity. So where does this appear? For example, in many applications, this potential here, let's imagine a general potential V of x. It can, for example, represent the density of charge of the medium. So if you talk about Rn, the density of charge of a medium cannot be constant in the whole Rn, otherwise the mass is infinite, the charge of the universe is infinite, so expect some decay of the density of the mass, for example, a polynomial decay. So this equation appears as a limiting case of polynomially decaying potential V of x, in which V of x decays of like 1 of x to the b. And so, for example, this appears, for example, if we try to do planar waveguides in an inhomogeneous medium, and of course, inhomogeneous variations of phenomena modeled by NS are also relevant here. And we're going to compare these two and give some information about this monotonicity that I want to talk about. So, for example, to begin with, since it's a Hamiltonian equation, right? So it has some invariances. So we know about Noether's theorem that some conserved quantities might appear. For example, mass appears by gauge invariance, by phase invariance. Energy, of course, itself is conserved. It's a nonlinear here, but it's a Hamiltonian that gives origin to the equation. For example, the momentum that comes from the invariance by translation. So these are quantities that are conserved with for the nonlinear, the classical one, not the inhomogeneous one. And besides conserved quantities, so for the INLS, we still keep that the mass conserves. The energy conserves, of course, we have to include this term here. But for example, momentum is symmetry invariance is lost because we have not translation anymore for the Hamiltonian, so we do not have momentum conservation. So we also lose other symmetries. For example, the NLS has many symmetries. For example, this is autonomous equation, so we can translate by fixed time, and it's still a solution. We can put a constant phase here and still keep a solution. We have a scaling invariance, so we can change the scale of space of time and add this nonlinear scale as well. And if U is a solution, this function is also a solution to the original equation. We can reverse time, at least in the mathematical setting, because we don't know how to conjugate a state in quantum physics, not a general state. But in mathematics, if we just pass the bar in the initial data, it goes back in time. For the NLS, we have spatial translation, and we have what they call the Galilean invariance, Galilean boost. We can change the coordinate system. We can give it a constant velocity, and it changes according to a Galilean, not a Lorentz transformation. For the INLS, we still have, for example, time translation. We still have phase invariance. We have scaling. Of course, we have to include this B here, but we still have a scale invariant equation, and we can still reverse time. What we cannot do, of course, we do not have translation invariance, and we do not have Galilean invariance because now the origin is fixed. The singularity is at the origin, it's not anywhere else. So we cannot give you the velocity and expect it to satisfy the same equation. And so this was a challenge at first, because many of the proofs that we had for the classical NLS would not apply here because we would make use of some invariances that are lost or some symmetries that are lost. But eventually you're going to see that this x to the b term is actually beneficial in some other settings. But let's talk about the first of all opposedness. To talk about the opposedness, since this equation is invariant by scale, so it has a scale invariance, we can talk about what we call the critical Sobolev index. So you can basically change the initial data, take any initial data and do a scaling that corresponds to the equation. So basically, time is equal 0, so we forget this part, so we put lambda x here and put some lambda to some power here. So we calculate the homogeneous Sobolev norm of this quantity. Since it's homogeneous, there's a power of lambda that can pull out, and then this depends on the equation, it depends on S. So if we choose S to be exactly this quantity, we're going to have a Sobolev norm that is invariant by scale of the equation. We call it this quantity then the critical sublevel index. And for those who are familiar with the NLS, if we take p equal to 0, so if we forget the p here, we recover, we get the classical sublevel critical index that we are used to. So this new model, it kind of just changes a bit the criticality. Why we talk about sublevel index? Because we're going to talk about well-posedness. So first, what do we mean by solution here? So we want to get HS solutions, which may ask it maybe 0, for example. We might not have any derivative, so we have to interpret the equation somehow. So we're using the Duhamel formulation. So if you can show, for example, if U is a classical solution, it has to satisfy some form of Duhamel term, Duhamel equation. Of course, U here and U here are the same. And we define the solution as to be a function that satisfies this equality. And this is the linear evolution. This e to the it delta is the linear evolution. So it's the evolution of the linear operator without the term U to the some power. So this definition, for example, enables us to define solutions without having, for example, a prior differentiability. We can talk about L2 solutions if we can solve this equation in L2, for example. And where do we have the local opposedness? So basically, it's a lot of parameters, but basically we have this power here. So P, which is the power of nonlinearity, it has to be between 1 and some limit, which is infinite in low dimension, but it's finite in higher dimension, which is related to the sublevel embedding in H1, for example. So we're talking about H1. So we have the critical sublevel embedding in H1, and we can talk about low poses below some index related to this embedding. B should be, so if B is equal to 0, then there's the classical NLS, but B can go up to 2, and you can show actually it's a recent result that if it's B bigger than 2, then we have ill-posedness. If B is actually 2, we still have ill-posedness. So we can only talk about B less than 2. And to those who are familiar, basically there's the condition on P, which seems odd here, can be translated to this, saying that the criticality, the regularity of the datum is bigger than the criticality of the equation. That's why we expect well-posedness. If this is equal, we call it critical, and it's a little bit more delicate, but we're talking about the subcritical. So this equation is well-posed in the whole subcritical region of indices. Moreover, so we have what they call Strichert's estimates. So basically, we can show that the solution is more regular in some sense than expected. So in the sense that the solution also behaves as some mixed space-time spaces with, it's the same level of regularity, but they belong to more spaces, so we call it local smoothing somehow. So this admissibility here we'll be talking later, we'll define it later, but there's a numerology associated to the Schrödinger equation. So basically, okay, so we have local opposedness. We know where this means that for any initial datum, U naught, there's a time t which is bigger than 0, such that the solution exists at least in this finite interval of time. And we want to understand, for example, if this time can be extended to infinity. So if we can have a global solution instead of a local solution. And first of all, we can find some particular solutions here, which are called the ground states for you. And the thing is, if you have a global solution, we want to know whether this nonlinear term here is very bad or not. So that's the idea. So how bad or how small or how big this linear term is. So if you expect it to be big, then it may interfere in the locality or globality of the solution. But if it's very small, then you expect that the solution is global. So we're going to define this the main topic of study here. So if you take any global solution, for example, we say that it scatters forward in time if the solution itself behaves as a linear evolution. So if there's some data, doesn't need to be the initial data. If there's some data in H1 such that the linear solution gets very close to the nonlinear solution gets very close to the linear solution, then we say it scatters. So basically, the nonlinear behavior is very small, It's what Ivan calls the boring behavior, because it does not blow up. There's nothing very interesting happening. So for this to happen, if you look at the Duhamel formula, this is equivalent to show that this integral here makes sense. So if we prove that this integral here is defined, then we can define the scattering limit as this, and then we know the solution scatters. But this thing is, this is an oscillatory integral. This is non-trivial to bound. So we need extra information on the solution to guarantee that it scatters. So we need some space-time bounds to make sure that this integral here makes sense. All right. So this is what we want to prove in many cases. We want to prove that given some initial data in a certain space, we want to know whether the evolution is global, and if it's global, if it scatters or not. So the first obstacle for scattering is the existence of the ground state. So basically, we can solve an elliptic equation. So this equation here is the time-independent Schrodinger equation, if you want, or some form of time-independent Schrodinger equation, which has radials, positive solutions. Actually, for HP and HSC, or HP if you want, in a suitable range, it has a unique positive solution, a radial solution. So it has many solutions, but only one of them is radial and positive. We can translate this to saying that given certain mass of this energy of this solution is the solution that minimizes the energy, so that's why we call it the ground state. But of course, we have many other bound state or excited states, actually infinitely many. But that's only one solution, which is positive and radial, and which in turn minimizes the energy, which we call ground states. So its existence was proved very early, in the 70s, a little bit less early for the INLS in the 80s. So it's basic, since this equation here comes from a scale invariant equation, so we can produce the so-called Wasstein functional. We can minimize some what we called Gallardo-Nirenberg inequality. So basically this is an interpolation inequality. We know that this weighted LP norm here can be bounded by gradient and F, so basically by the H1 norm. So if we find the best constant for this inequality, we can actually find that it is achieved by a solution, and we can prove that there's a list solution of this, and we can prove that there's a unique positive and radial solution to this equation. So it's many steps. Yeah, please. Yes. So because it's invariant by scaling, so we can fix any eigenvalue, and we can show that by scale invariance it's equivalent, because basically we take this. So if we find this solution, the solution to this equation, we know that the standing wave here is the solution to the NLS. But you can change its frequency, meaning that I put one here. So this equation itself, like this, has a unique positive and radial solution. But of course, if I want to put a 2 here, then there's another unique positive and radial solution, which is related to the original biascaling. So we know exactly the curve of eigenfunction somehow. Yeah, we can do this because we have scale invariance. If we didn't, then we should have put the omega here and then try to find a solution varying omega. All right, so we minimize this inequality, we find a ground state, and we know that this guy here, which is periodic in time, is a solution to the equation. So this solution here, which belongs to H1, does not scatter because it doesn't have a linear behavior. It's periodic. So we know that, for example, for dispersive equations, the solution needs to disperse. So if it's smooth, if it's in L1, for example, its linear evolution must go to 0 in L infinity. As time passes. So this is clearly not scattering solution. So this is the first obstacle for scattering that we encounter in our equations. And actually, we can prove something bigger. Basically, we call this quantity of this ground state will give us what you call a threshold for scattering. So basically, since we're using a scale invariant equation, it's natural to use a scale invariant quantities. So it's more beautiful to write this statement. Yeah, here's a question. Yeah, sure. A subcritical P. So the same P's that's considered subcritical, which means this P here, up to this P. Yeah, so up to infinity in low dimension, of course not infinity, but less than infinity in lower dimension, and less than this in higher dimension. And this is related to this, of course, the validity of this, this Sobolev embedding here, or this Galeano-Nebengu inequality here. Of course, if P is very large, then this is false. And then we need more derivatives here to control this quantity. So we define some scale invariant quantities. So we take the mass and raise it to the 1 minus SC, multiplied by the energy to the SC. So this guy here is scale invariant. We want to normalize it compared to the ground state. So we divide by the same quantity calculated at ground state. We call this the mass energy. We also call the mass kinetic energy, which is the same with the gradient here, the altitude norm of the gradient. So this is not conserved. So this depends on time. The energy is conserved, the mass is conserved, but this is not conserved, so this can depend on time. With these two quantities, we can give a threshold for global existence, for scattering, for blow up in this following sense. So basically, this started in the subcritical case, which we are working. We're not talking about the critical case, which has some subtleties. So in the subcritical case, we started with the Romer and Rudenko in 2008. Then Luccas entered this group and did so first they did the radial case, then they did the non-radial case for the 3D cubic. And then the student of Svetlana Rudenko gave more general classifications, and also Fonseca Zenave did a lot of work. So this is a big theorem made by many hands, which says that in any dimension, in any criticality between S0 and 1, which means that we're above the L2 critical and below the H1 critical equation, and we get a solution with small mass energy. So less than 1 means we are prohibiting the ground state itself, because we have to have energy less than it, mass energy less than it. So in this case, if you have low energy, we can have two possibilities. Either we have a high initial kinetic energy or a low initial kinetic energy. So if you have a high kinetic energy at the beginning, and we need some actual localization, so we need to some extra decay or some radiality, otherwise the result doesn't hold as stated. But if you ask a little bit more decay that H1, then we know that the solution blows up in finite time, meaning that it ceases to its H1 norm goes to infinity in finite time. So it ceases to exist in H1 if you have high kinetic energy. But if you have small kinetic energy, then the solution can prove that it's global, and moreover, that it scatters in both time directions. So this is for the NLS, is very well known since the 2000s, 2010s. And it's not an easy theorem to prove, especially the scattering part. It's non-trivial. The blow-up part is a little bit more achievable. The global existence is more achievable. The scattering is just another theory. And for the NLS, of course, we do have a similar result with some extra restrictions, especially because of the parameter B. So this also has many people working on. So basically, but it's basically the same thing. So if we have low energy and high kinetic energy at the beginning, some extra localization or dimension 1. So in dimension 1, you don't need some extra decay. You can prove scattering without any additional hypothesis. Then the solution blow up in finite time in both time directions. And if the mass kinetic energy is smaller than 1 and dimension is 2 or higher, so this fails in dimension 1 because we have this 1 to the x to the b, 1 over x to the b. Even if b is very small, if you differentiate it, we get 1 over x to the b plus 1, which is non-locally integrable in R. So unless the solution belongs to some weighted space, we do not expect it to, not even well posedness, because of this technical remark. Of course, we have to restrict a little bit the power of B because of this functional space is what we want to work on. But this, so now it's proved, one of the proofs is given by the method I'm talking tonight. So we can prove that the solution is global and scattered in both type directions. So that's what we want to prove this statement 2 of this theorem here with this argument. And so it's very known in the dispersive setting and also in other settings, what we call the concentration compactness rigidity approach that was introduced by Koenig and Murr, and also 2006, I guess. And it's a lot of steps. So we inherited it from the elliptic theory. So we had the profile decomposition that they call it maybe bubble decomposition or the concentration compactness approach by Pierre Lyon and collaborators. And we inherited it. We want to show that the solution scatters. So how do we show that the solution scatters? So that basically any solution in a certainable range scatters. So we assume that it does not scatter. So we have some type of induction of the mass energy. So, well, if not every solution scatters, then we can get the smallest one which doesn't scatter. And we're going to work on this limiting or critical solution. So for this to exist, for this equation to exist, for the solution to exist, it's a lot of work. So we assume, for example, that there might be some solution that does not scatter. Then we apply, so there might be a sequence of solutions going to some critical value that in each of this solution does not scatter. Then for this sequence of initial data, we perform what we call a profile decomposition, which is somehow describes the lack of compactness of some embedding, for example, the Sobolev embedding or Stricker's embedding or the operator embedding. We also rely on what we call wave operators or asymptotic completeness. So wave operators, when they exist, they say that, well, so we're trying to solve the scattering problem. So we try to solve, given as initial solution, initial data, does it scatter? So does there exist a final state for which it scatters? The wave operator is the opposite. So given a final state, can we find an initial solution at a large time that scatters to it? So it did some asymptotic completeness. We need to be able to sum. This is a nonlinear problem, so we cannot sum solutions, but somehow we want to sum them and get an approximate solution, which is good enough for our purposes. So we need some time of what we call long-time perturbation, of stability, in the sense that if solutions are far away, they do not interact very much. If we sum them algebraically, so give the sum of them, is it approximate solution? And what are the properties we can expect of this related solution somehow? So all of this lead us to what we call a critical solution, which is basically the minimum counterexample for scattering. So we built all of this to get one critical solution that does not scatter. It's the smallest one that does not scatter. And we show that the solution is so good that it cannot exist. That's what we call the rigidity. So it has to be 0, so we're done. So with our argument. This is a very powerful argument. It's very robust. It can be applied to many equations, but it takes a lot of effort, a lot of opportunity to be built. And we're going to give here a simple proof of scattering. And it was given first for the INLS because the other, this method was not available to the INLS due to the lack of symmetries, the difference of symmetries between a linear operator and a nonlinear equation. So for first we're trying to understand so to apply this technique, and we stumbled upon this problem, but we changed the approach and could prove scattering with another approach. After that, we had people proving scattering with this approach here, but it was much later. So let's basically that's the question, right? So can we use another technique to prove scattering below the threshold for any P and B? So in the sense that, can we prove this statement for the INLS? And the answer is yes, as long as we can somehow beat Sobolev. And I'll be clear in a moment. So what do I mean by beating Sobolev? But that's our objective right now. And to beat Sobolev, or to beat the Sobolev embedding, we're going to need some monotonicity formula. So that's what we call. So first of all, the assumption that the mass and mass energy and the kinetic energy are not big, they're useful in the following sense. So if we know that this is less than 1 and this is also less or equal than 1, we can prove that actually the whole evolution does not approach 1. So if we have initial datum, U0, U0, that has low mass energy and low kinetic energy, actually you can prove that the solution is bounded in H1. And since it's bounded in H1, you can show it's global because we are in the subcritical case. So basically, this is what we call the global coercivity. So this assumption that the energy is not too big prohibits the ground state so much that it cannot get even close to the ground state. That's what we call the energy trapping. And it also, so as byproduct of this, the proof of this also gives us the following coercivity bound, which says that we can, under this assumption for ADT, we know that this difference here, so this is a positive term, so this is actually difference, is bound by above this quantity here. So this quantity here is bounded by this quantity, and this quantity is useful to us. It's what we call the virial quantity, and it appears in our arguments. So we know that it's positive, and more than positive, it's coercive. So it controls this quantity here. Question? No, it seems to be an incompatibility, but it actually, it's a byproduct of the proof. So basically, we could not have equal to 1 here. You know, sorry? So if I choose the initial data in this setting, so this, okay, it's dishonest to write it here, but this basically says that it could not have been equal to 1 at any time. So, yeah, but well, I should. I mean, it's just to write in the slide, but you're right. This argument is very interesting. So basically, we use the conservation of the energy and this Gallardo-Nirenberg inequality here. So we want to bound. I can at least make a drawing here. Do I have a chalk? Yeah, I do, right? So the thing is, we write. It's a very nice drawing. So we know, for example, we know that the energy of the initial datum is any energy and any time, and we know that's basically the kinetic energy minus the potential energy. Let's say for the NLS. All depends on T. And the other integrals are in space. So we bound this by Gallardo-Nirenberg inequality, gives us plus or greater or equal. So we have this minus a constant that comes from Gallardo-Nirenberg. And then we have this to some power. How do I I mean, it's some P plus 1 times 1 minus theta. And then we have the mass, which is conserved, to P plus 1 times theta, something like this. So this is a constant, and this is a power that is bigger than 2. So this is 2, and this is bigger than 2. So if you call this, for example, x of t, this is going to be x of t to some power bigger than 1. So we say that's 1/2 x of t minus a constant, another constant, it doesn't really matter here, x of t to p plus 2 some power q, in which q is bigger than 1. So we know that for all times this must happen, and of course, if you have the times the mass here and have the ground state here, what we have is that in any time, the function f of y, which is basically 1/2 y minus constant y to q, applied on x on the kinetic energy should be bounded above So what we do, we draw the the graph of this. So if this is bigger than 1, then at 0, this part wins. So it's basically linear. So it behaves basically like this, close to 0. But if y goes to infinity, this dominates. So it eventually has to do like this. So we know that f applied to x of t must be below some quantity which is conserved. So if we take this quantity to be below the maximum, which happens at the ground state because equality is achieved, so we know that I have a potential well here somehow. So either by continuity of the solution, either we are trapped here or trapped here. We cannot move between the two. So, and this is where we get this 1 minus delta. So that's where it comes from. That's what the Kenningham model called the energy trapping. So basically, yeah. So we know that the solution is it's bounded if it's bounded, it's defined for all times, and we have this quantitative coercive. What we do, we have what we call the VR identity. That's the monotonicity formula I wanted to talk about. So if you get any smooth weight, if it's graded, it's bounded, then you can define this quantity here that comes from conservation of momentum, truncated somehow in space. If we define this quantity, which is well defined because this guy is bounded, then we have Cauchy-Schwarz, and we have an H1 solution. We can differentiate it on this on time and get this beautiful equality here, the identity. So we have some kinetic terms here, some potential terms here, a mass term here. And what you want to do, though, the classic argument for proving, for example, blow up in the 30s by Glassy was to take, for example, at least formally A to B x squared. So absolute value of x squared in Rn, so the gradient is 2x, then the second derivative is a delta, and we get exactly that quantity that's coercive that was in the previous slide. Of course, we cannot do this here in this setting because this guy here is not bounded, so this functional here might not be defined, but it gives us a hint that we have to localize. So we can define, so if we're going to localize, we need some localized version of the coercivity. But basically, if we start a little bit 1 minus delta and also less than 1, we can get a large ball and cut off to this ball, such that the solution times is cut off. We lose a delta here, but we still have a delta, so it's still bounded away from the ground state. So, and this is simple to prove, given the original coercivity and the boundedness in H1. So this is basically an easy lemma, and of course we have a local version of that lemma as well. So we have a coercivity in a localized version. So we have a cutoff multiplying the solution. And we're going to use this to define a new weight. So it behaves like x squared in a large ball, which we will define later, and then starts to evolve more linearly outside a larger ball. So we have to glue it accordingly, but we glue it in the A should be radial. We're going to get it never decreasing and never concave down. And also we have this is we can produce weights with this decay here. This is only in the intermediate region, so it's okay. But basically, so it's x squared and x. That's what we want to do. And this weight is now has a bounded derivative, the bounded gradient. So, and also if it has a bounded gradient, of course, it depends on the size of the ball and the limit of on the bound of the H1 norm. But besides that, we have, of course, a truncated version of the VR identity. So since everything is local, we can calculate it inside of this large ball and outside of this ball. So I have many error terms that we want to control, right? So this is a localized version somehow of the coercive quantity, and we have to treat all of the other terms. So the easier terms, for example, to throw away are this. So this is a radial derivative. This guy we choose to be positive, so this is This has a sign, this is positive, no, negative at least. This is what we call the angular gradient. So it's the gradient projected in the non-radial direction, the direction perpendicular to the radial direction. This also is positive, so we can throw it away, even in the non-radial case. So if it's radial, if U is radial, this does not exist. If U is non-radial, it's still positive, so we can throw it away. The more I differentiate the weight, the better the decay. So this guy is going to be bounded by the mass divided by some power of the radius. And this guy's here. So if we have this term, beautiful term here, we are outside of a ball. So we can just take the supremum. If this guy is zero, be zero, and the classical analysis, to use this argument, we have to assume some radiality, for example. So we have Strauss inequality that gives us uniform decay on R as well. In any case, we have this coercive quantity in the ball, plus some decaying terms that decay on R, but not on time. So we have constants that depend only on the initial data, and then we have uniform decay in space. And what do we do with this? So basically, we can, since we have this, we can integrate. We can use the fundamental theory of calculus to integrate this to get and take it divided by t to get a nice bound like this. So basically, times t divided by t. So and this guy here is bounded. So that's how we get this term here. The other terms are like exactly like this. And this is inside of a ball. Outside of a ball, we have this guy here decaying again, or we have radiality. So we also have basically the same bound, and we can sum these inequalities to get this what we call the Morawetz, Virial-Morawetz estimate. Here, there's no radius anymore, so we can choose any radius. In the right-hand side, we choose it slowly increasing, so everything decreases on time. So what we have here is that on average, the kinetic energy of the solution must decay on time. So as time gets larger, this average goes to zero. So that's what we call beating Sobolev, because if you use just crudely Sobolev here, this guy is bounded by the energy, or by constant times the energy. So we get 1 here. We get no decay. So we use the monotonicity formula to get some decay, and with this decay, we're gonna prove scattering. That's the main point of the talk. So I think I have like 20 minutes. Oh, how much? 10 minutes? Okay, thanks. I cannot sum. So this inequality here gives us some extra things. So it gives us, for example, that this should be a lim inf. It's a typo. So the lim inf on time in a large ball, or for any ball, should go to 0, and also a mass on a large ball, the lim inf should also go to 0, using the mean value theorem. That's basically the last inequality and mean value theorem, but along the sequence, not the Holder limit. And what we do with this, so we have this beautiful scattering criterion that was introduced by Tyrestyle in 2004 for the cubic NLS, then was exploited by Dodson and Murphy in 2017. We also give some contribution in 21 that says that if you have any solution to the INLS or to NLS, but to NLS we have to assume radiality, such that this guy here is bounded. We know that it's bounded, for example, if mass energy is small, if mass kinetic energy is small. Then, if on a large ball, the mass becomes small for many times, then we know that it scatters forward in time. So we did all of that job, all of the work to get the lim inf of the mass going to 0 to apply actually this criteria. So if in a large ball the mass escapes from a large ball for many times, then the solution should scatter. That's the statement for the radial NLS or for any INLS. And the proof of it, it's not complicated. It uses basic, but it's not that it's not complicated. Usually it's short, but it uses all the theory we have. For example, it uses what we call the dispersive estimate. So we know that the linear evolution in LP spaces decays at a certain rate in time. We have a notion of, this gives us a notion of the admissibilities. We know that there's some numerology that says that if the time index and the space index are related by this equation, of course we have some endpoint which is not available here, then we can define, for example, for these admissible pairs, a Striker's norm, a dual Striker's norm, and we have the so-called Striker's estimate. These are they call exotic Striker's estimate. They are not the usual ones. Usual ones are usually with S equals 0 here, but we need more, so we need some S between 0 and 1. Please. Yeah, but this is a linear. Yeah, but so the thing is, it's a radial NLS, so solutions should be radial. Yes, or the INLS, which doesn't admit a traveling solitaire because it has no Galilean invariance. Of course, for the non-radial NLS, you need more powerful tools, but so you can have a more complicated version of this criterion, which uses the so-called interaction estimate. So we do the tensor product of two solutions of the same solution and put an interaction function between them. Then you can exclude the, of course, but yeah, you're right. If it's a non-radial, then it's of course false. That's why, for example, this theory doesn't work for the KDV equation because in the KDV, the solitaire must move. So you should ask for something else. You can ask in the known areas, but it's not very useful. You can ask that in any ball which with size R, it becomes small. So we take the supremum over all the balls with same size. And it excludes the solitaire. We can prove criterion, but it's not useful. In the sense that we cannot show that this hypothesis this is too strong. Yeah, you take supremum of any balls, it should be small. This happens for the scattering solutions, doesn't happen for the ground state, and we can show it's a scattering criterion, but not useful. So we have a notion of the admissibility. We have Striker's estimates for the linear term, for the inhomogeneous term as well. So we can use Duhamel here. It's okay to use Duhamel here. And basically, we have what we call small data theory. So we are above the electrocritical, below the electrocritical, so we have what we call small data theory in the sense that we take a bounded solution, and if its linear evolution in this Striker space is small, we know that it scatters. So that's what Thierry Cazeneuve calls the small oscillating terms. So this guy here, it's strange. This S here doesn't involve any differentiability, just to show that the scaling of this norm is the same as scaling of this guy. But it's a space-time norm with no derivatives. So if we bound it, if we calculate this norm and it's very small, then we know that it uses scatters in each one, and that's what we want to use. So basically, we split the Duhamel term in 3 terms. So we want to take U at a very large time, evolve it linearly, and then understand what happens after that. If this evolution here is small, then we are under the conditions of small data theory, and then we have scattering. So what do? We calculate the linear term and then split the interval in 2 parts. This so we have very many parameters here. We have T, we have epsilon, we have alpha, but this guy is smaller than this one. And we have what we call the recent past between T minus something and T, and the distant past, which is between 0 and T minus something. We split this interval in 2, and we're going to use the massive equation here in this part. We're going to use the dispersive estimate here in this part and show that all of these 3 terms are very small, if we choose time to be big enough. Then we're going to conclude scattering. So for the recent past, we can localize in a ball and outside of a ball. If we're localizing a ball, we can use the criterion that the assumption of the criterion that there's a sequence of times in which the mass is very small. So this is very small, this is bounded, so this is a very small quantity. If you're using the INLS, so this x to the b also helps us by giving us uniform decay here. If you do not have uniform decay, if you are the NLS, we have to assume radiality, and then we have uniform decay again. So basically, this quantity is very small, this one is bounded, so we have some smallness here for the recent past. And then we interpolate this because these are subspaces. We calculated the Striker's norm is also somehow bounded. Then we can use, for the distant past, there's a magic trick here that says that if we write what is the distant past, so the integral between 0 and this, calculated at this time t here. So basically, we can show that this actually is a difference of 2 linear evolutions. So you can use Luccas estimate to interpolation to put in this space here, which gives us the boundedness, and this space here, which enables us to do some explicit computations. So note that this is bigger than the Sobolev embedding critical index. So we're somehow above H1, but we're not using it. But we're using the dispersive estimate too. So this guy here is going to be bounded. We're going to integrate this and say that since this power is bigger than 1, it's going to be integrable at infinity, and we're going to have some smallness here again. So the tail is going to be small if capital T is large. So basically, and for the linear term, of course, the linear term also goes to 0 by Luccas estimate, so everything's very small if we choose T large enough. So we conclude that this linear evolution here is small, can be as small as we want, so we're under the conditions of the scattering criterion, then we have scattering. So that's the main thing. So just to give a final remarks, basically we proved that under some restrictions on P and B and the smallness assumption here, not too small, right? So it's explicit, so it's under the threshold given by the ground state. We have scattering in both time directions. And, oh well, that's what we used. No, I think it's, oh, so I give you the wrong, wrong slide. So basically, what we know is basically, so this was used by many authors. So this can be extended to Schrodinger equations with the potential. So instead of Laplacian, Laplacian plus V, and we have V under certain conditions. We can have some non-local operators on the nonlinearity, for example, the Hartree equation or Hartree-Fock equation. This has been extended to the bilinear, to the fourth order Schrodinger equation. So it's Laplacian of the Laplacian, it's Laplacian square. And so this technique is very simple even to explain it here. It proves scattering, and it has a wide range of applications. If you want to go to the critical case, which avoided here, we can still use it, but we have to put a lot more effort because we need to use the concentration compactors plus this kind of Vilker estimates to conclude that we have scattering. But it still has used, for example, Benjamin Dodson has used it to solve open problems. For example, the NLS in the H1 critical case was in the fourth dimension was open until 5 years ago, I guess. And it was a paper by Dodson that used this kind of monotonicity estimates or Morawetz estimates to conclude what he wanted. So that's what I wanted to talk. Thank you for your attention.
So any question? Yes.
The L2. So yeah, it was solved by Dodson as well. Yeah, the L2 for the NLS was solved in any dimension by Benjamin Dodson. And the NLS was recently solved by, yes, you have to do form as well. Yes.
A question? Yes.
Yeah, you could use more general. So so this it has a radial decrease. It's radially decreasing. This is the main. Yeah, the thing is, you're gonna have to change a little bit the statement maybe. First of all, I have to know whether there's a ground state or not to get a threshold, right? So I have to solve the elliptic equation, but other than that, yeah. So you lose the concept of scale invariance. So maybe if you say that it decreases exactly as x to the minus b, then you can somehow recover the critical index. But other than that, you can use more general potentials, especially if they decay and if they're positive and radially decaying. If they are not if they start to increase radially somehow, then you have trouble with the Vilker. But that's a nice question as well. But it might not be. Well, also might scatter. because it gives you the defocusing characteristic. So yeah, I mean, more general potentials are still open.
Any other question? If not, let's thank Luca again. And